All right, welcome everyone to my second webinar of hopefully many. I'm going to be speaking today about comparison of commercially available methods to measure ultrasonic transducer displacement. So with transducers in general, there are electrical measurements and there are also mechanical measurements. A lot of times the mechanical ones are easier to understand, although they can be more expensive. There are a lot more options there, but it's easier to appreciate, and because of the options, it can be kind of confusing as to what you need to purchase and what options exist. And hopefully, by reviewing all of the different options and why even measuring displacement is important, I think you'll come to a better appreciation as to fully utilizing the tools you already have and potentially learning about new tools that may be better for your application, either from a price perspective or from a capability perspective as to like what you want to do next. Or if you just like, how do I get started measuring displacement for the lowest cost possible? That's also something I'm going to be covering today, and kind of where the what some of the general kind of trends are with some new technology as well. So with that, I'll go over why we measure displacement and vibration, what parameters are important when considering what to purchase or what you need to be looking for in your system. And also comparison between different systems. Today, I won't be particularly, since I don't represent a, a measurement company who produces measurement equipment. I hope that this presentation is going to be a little bit more well-rounded and honest, rather than a sales engineer trying to pitch you perhaps the most expensive product they have, and not knowing really in detail how your products work or what's the good and bad parts about them can lead to misuse. Devices aren't simply point and shoot as you would like to believe. So there's a lot going on in terms of the analysis. So we'll go there. All right. So again, why we measure displacement, what parameters are important in comparison between devices, and some kind of final say and verdicts. I also provide, alternatives to measuring vibration. If that's either not particularly useful for your system, or it's cumbersome, or it's too expensive, there are also other methods of understanding how much mechanical energy or forces are involved in your particular application. So firstly, why measure the vibration, which I'm talking about the displacement or the velocity of your ultrasonic devices? Why is that important? Well, vibration or oscillation, mechanical oscillation is actually the point. It's not simply just to power your device with a certain frequency. You're looking to make an impact, you're looking to make a particular physical function in the real world, and that happens through the electrical mechanical conversion of piezoelectricity from voltage then to force or displacement, as however you would like to phrase that. And when you're measuring, a lot of applications, you might be measuring current and power or voltage. Those are just indicators of vibration. You can actually achieve, voltage and current and power through a resistor. But the difference is that the resistor is not converting that into mechanical motion. So vibration is actually the point. So maybe one might say that, hey, if I only have one measurement I can do on a transducer, I'm gonna want to measure its vibration, its oscillation state. Although that there's a lot missing from just oscillation, it's sometimes more cumbersome. There's, for example, so many different points you could pick to measure that. It's really the point of the whole product or device is to produce vibration. The other reason for measuring oscillation levels is to verify your finite element analysis. You can do impedance and you can do frequencies, but really the mechanical part is an essential portion of understanding how your finite element model is working. and then and to verify that according to amplitudes and also spurious modes, which I'll mention here. So a lot of times these spurious modes are not very well electromechanically coupled. However, they can provide a lot of detrimental results for your specific transducer. They can take away energy from the main mode. They can also cause failure. So for example, some ultrasonic transducers, they have electrodes like tabs sticking out to power the piezo ceramics. Those tabs can undergo oscillations where they can, it's not really detected very well using impedance, but it's detected very easily using a vibrometer, a basically a displacement or ultrasonic transducer mechanical measurement. It can also help to determine the relationship between current and vibration. So here's like a common kind of metric, and I especially know this from the medical device field, where you want your surgical instrument to achieve a certain level of displacement, but you don't have any way of measuring it live, obviously. So it works out that at resonance, for a resonant ultrasonic device, that's sufficiently has sufficient Q in coupling, you can actually determine a fairly consistent displacement to, or velocity, however you'd like to look at it, a displacement to current relationship. So if you know, for example, I'm putting in 30 milliamps of this device, it's going to produce between 30 and 45, let's say, microns of displacement. That's my tolerance. So it's a very good metric for putting in your data sheet, for putting in your product specifications. It works out quite well there, and it allows you to standardize your products and know how much energy and force you're putting, you're developing. It also helps in looking for nonlinear behavior explicitly, which can tell you about incorrect operation of your device. For example, if you're working on a bolt clamp Langevin transducer, it may indicate that you are reaching a limit of a performance. It helps to explain a lot of other things such as fatigue and failure, fracture as well. It can occur in the current signal. You sometimes you are able to find that measurement of nonlinearity in current, but it's extremely prevalent in vibration itself because it's a pure mechanical measurement, whereas current is both contributed toward from the dielectric and the mechanical response of the oscillating crystals. In fact, from your vibrometer or whatever displacement measurement method you're using, you can actually target different points. So if you just go 2 steps back here and look at this transducer, when you're taking electrical measurements, you only get measurements from this piezo stack here. You can't measure, and that's kind of more of like a bulk measurement where you'd assume that, hey, the response of the piezo ceramics is going to representing of the whole system. That's like a whole system measurement. You have one terminal to check. Whereas for vibrometer measurements, you can measure the entire system. You can measure the displacement at the tip. You can measure the displacement at the flanges, specific and other specific points, looking for either failures or looking for things that aren't operating according to expectation, which can lead to insight and change in your processes or your construction of your transducer. So you have a lot more choices, which actually makes it more complex and confusing. But because obviously there's only 2 terminals for usually for your electrical drive, so it makes it more confusing, but it can also be quite powerful as a mechanical first measurement. Yeah, feel free to put any questions in the chat that you have as we're going through. This is a little drawing I made a while ago, but anyways, I digress from that. So what parameters are important to consider when you want to measure vibration, when you want to measure oscillation or displacement? The first question you need to ask yourself is, do you need displacement or do you want velocity? And you may think that, well, what's the real difference? All we have to do is, multiply the angular frequency by the velocity, or by the displacement, we get velocity, or we can go either way as long as we know frequency. So that's true. So I'll talk about a little bit more of that in detail in the next slide. But some of the considerations, once you determine whether you need velocity or displacement, you can understand if you want the minimum or maximum. What's your minimum velocity you want to measure? What's the maximum displacement? Those ranges are very important. There's some of the measurement techniques cannot measure very low displacement. Some won't be able to measure very high displacement or velocity. You also have to understand your maximum frequency that you're going to be interested in. As a transducer consultant myself, because I work on many different types of devices, it's hard to purchase a product it's hard to purchase a reasonable costing product for the wide variety of transducers I work with. So usually my clients have their own measurement systems for vibration, with some exceptions, because some clients may work in the 200 kilohertz range, one may work in the 40, one may in the megahertz. So there's quite a variety, and as you go higher in frequency and obviously and maybe higher in displacement and velocity, things start to get much more expensive. So it's kind of hard to plan for all clients personally, but you definitely, for your own application, whether you're a megahertz device or whether you're in 40 kilohertz. You're not going to design a device 100 kilohertz, so that it makes it much easier for folks probably like yourself. So here's kind of a fun fact here. It was like a 1 second, excuse me. All right. So a fun fact here was, well, a cheetah can run 29 meters per second. So if you looked at an ultrasonic transducer, what would be the displacement that an ultrasonic transducer would need to oscillate at in order to equal the velocity of a cheetah? Now the ultrasonic transducer is going up and down, so it's kind of its maximum velocity on the way over to the other side as it's oscillating. But it would have to, if you had a 40 kilohertz transducer, it would have to oscillate with 115 microns of displacement to run as fast as a cheetah, which is kind of I find it amusing. Just to note how transducers compare to results from the animal kingdom. And I think this would be rare for a transducer to be at 115 microns. Very typically, the lower the frequency, the higher the displacement that can be achieved, because as you increase frequency, acceleration, velocity increases by a factor of omega, by a factor of the angular frequency, but acceleration is by 2 factors, or by omega squared. That creates a huge acceleration and kind of stops amplitude from really being something practical, which can actually happen because of the forces generated, the inertial forces generated there. All right. Obviously, let me know if you have any questions. So let's talk about here velocity versus displacement. So who wins out on this? What's more important? So the first question that I kind of ask, like, why measure some of these devices that I'll talk about, the measurement systems, they either measure displacement kind of as a primary function, or velocity as a primary function, and then displacement as a secondary. So it is important to know whether you want displacement or velocity. More often than not, you want velocity. But let's talk about that a little bit. So why measure displacement when velocity can be integrated to measure displacement? Because you just basically do basic calculus. You put the function on your oscilloscope. You run your function in MATLAB, and you think you're probably pretty good to go with one or the other. So I'll mention a couple aspects here that are important. The first is bandwidth, and I forgot why I wrote that. But I might get back to that if I remember. So the integration of air. So what do I mean here? If you have a displacement of high frequency, and this also goes along with multi-frequency signals. So if you have like a slow change in displacement, but superimposed upon an oscillating kind of a high frequency oscillating signal, then that kind of bulk displacement will then have a lot of error if you actually integrate that back through velocity. So basically, measuring displacement first allows you to capture, you could say, a wider range of frequency signals, like a slow changing position along with oscillation. So if your transducer is and this would only really happen for an ultrasonic motor. This is very important for an ultrasonic motor to be measuring displacement at the same time as understanding the oscillating motion as well. That's actually that's actually the most important kind of consideration. Usually for devices that aren't working as an ultrasonic motor basically, or linear motor where you're actually moving something, but at the same time there's oscillation happening as that's occurring, so you want to capture that low frequency slow change as well as the high frequency oscillation. That's really going to be the more important step. So here's like an example where in 1 second the motor moves 1 millimeter, which is very slow, but with the ultrasonic transducer actually moving at 1 meter per second. I'm gonna put on my 1 second. Let me just pause the recording. Yeah, so measuring these two wide scales is not going to be possible using velocity because the velocity is actually quite small. But although you do have this level of change in displacement occurring. So there's also that chance of error, and if absolute position, I guess one could like understand their own application if absolute position is important to be measuring, and that's usually more important again for ultrasonic motor where you're trying to where you're trying to understand displacement, like kind of a bulk change along with oscillating motion. Here's kind of a refresher plot. This is amplitude versus frequency. And these are non-dimensional plots here, hand-drawn by yours truly. So D here, this red curve is displacement. This blue one is velocity. So this is kind of just a refresher on what happens. So let's say at low frequency, let's take a piezo element or something. Let's say this is a piezo ring or something like that, and it's oscillating. For a given voltage, it will have a very constant displacement across, let's say the resonant frequency is 40 kilohertz, across 1 to let's say 35 kilohertz, it'll have a very constant displacement. However, due to the increase in frequency, the velocity is now going to dramatically change. When it's a really low frequency, it's actually going quite slowly, therefore the velocity is practically zero or very small. But as you reach the resonant frequency, both displacement and velocity peak. After you get out of that resonance and you start to exceed the resonant frequency, and let's just only consider this resonant frequency, your oscillation level, the displacement will quickly start to head towards zero. Won't quite get there until you get to your next resonant point, which is another story, which I'd love to tell you about someday. But and then the velocity kind of rolls off at a lower rate than displacement, because the velocity still, as you're increasing in velocity or in frequency, you're still kind of giving that little bit of a boost to velocity due to the increase in frequency, but that same boost is not given to displacement. Kind of as a general talk about what you're going to be expecting. So one would actually think that, yeah, if I'm measuring a high frequency device, it's likely going to have low displacement and high velocity. And that's actually a problem for one of the specific methods I'm going to describe, which wants a certain level of displacement. And without further ado, I thought I moved this slide around. I thought I moved it to the end. I did, and I copied it. All right, we'll just start with the different types of devices, and I'll just start by talking about companies that sell them. Although there are many companies that sell laser vibrometers, as you can see here. This is what the basic setup looks like. There's like this big control box, which is probably as big as an old school. Actually, it's about the size of a computer a PC tower sideways, just to give you an idea if some of you don't know. And then there's usually another kind of a laser module that comes out of that from fiber optic cables. So the company I have shown here is pretty much the I would, at least from my experience, it's the best provider of this technology, the laser Doppler vibrometer. But there are also other vendors, as you would imagine, at different price points. and some different capabilities. They're also the leader in cost. This is the equipment that I've had a lot of personal experience with. So this is what I started using in my PhD. It's a vibration first measurement, but they also have like modules and I guess high speed decoders to get displacement, so it can also measure displacement well. So it has that capability. The thing I really appreciate about this is that it is analog, that you can plot your current and your voltage waveforms along with your vibration to actually make sense of all of them at the same time. I find that to be invaluable for research. So this has a really good capability for scanning, like this vibrometers in general, because they don't have to be up close and personal, as I'll describe some of the other methods. You have to get extremely close to your target in order to make a measurement. With this, you can have a standoff distance. There are mirror systems that and I'm just doing this because I have no images of it. I don't have the system, so I won't be able to necessarily show it in action, although I probably could have found a video. But there's a mirror which then hooks up. It's programmed through to pretty sophisticated software, which can match phase angles and give you multiple measurements and give you kind of an image of how your transducer is oscillating. So you might see the tip of the transducer looking like this, coming out of the page, or something like that. So yeah, if anyone has questions about what that might look like, yeah, feel free to kind of ask for more, and I might post a video about it too later. So there's lots of unique accessories and software. One of the unique things is like there's a microscope attachments that you can measure MEMS devices, for example. So it provides a lot of capabilities, and for a lot of folks, this is the only option. Like going for the vibrometer, going for a scanning. If you need scanning, the choice is done. You have no more choices basically. So, but what I don't like about it is the price. I personally am not going to buy one of these. At least at full price, and they're not exactly compact. So they do take a larger space than most electronic equipment. They're certainly larger than an oscilloscope, and oscilloscope and obviously voltage probe is what you use to measure voltage, right? So that's really small compared to something much larger. So it's not desk friendly, but it's definitely manageable and it's used, right? So I'll spot myself too. Okay, so let's keep going here. Okay. So I don't like the price. The price is, $20K or $30K plus, $30,000 plus. Usually, even for the kind of basic module for the scanning, it can get into the $300,000 range. So it's definitely like for research institutions, almost always. Although there are production environments, and I personally have witnessed it from previous positions I've had in industry. There are production environments that use scanning vibrometers on every transducer that's shipped in order to ensure that there are no spurious modes. It's simply because of the high power that is utilized for those transducers. There's not really room for known defects to be present at all. So the higher power your transducer is, the more likely you'll need to do more characterization to ensure that everything is working smoothly and correctly. This is another kind of discovery. I guess not really discovery, but it's a different type of device altogether. It's not a laser device, it's a light device. It uses light reflection in order to measure displacement. So this is what it looks like here. So the module is quite small. It is kind of probably about sort of the size of like a power bank. You could say a larger power bank. Or maybe, yeah, so that's about how large it is, like this module here. The tip, as you can see, the fiber optic tip is actually it's pretty small. It almost seems like something similar to the vibrometer. However, the difference in this technology versus the vibrometer, the biggest difference, there's two. One is I mentioned it's a displacement device. So the closer you get to your target, or the farther you'll change the voltage reading. So this direct voltage, so it's also analog. So these terminals here, they're voltage. So this is what happens. So if you took your sensor and you moved it closer or farther, like if you have it from really far away, like let's say over like here, you'd slowly, when you start getting to our device, when you're 1 millimeter away, you'll have a little bit less than 2 volts, and when you reach this point, you'll have 5 volts, and when you as you get all and when you get really close to your device, you'll have close to 0. So what you actually notice is that, well, this is kind of a funky curve here. We got to do something with that. You can't just like use this full range. So that's true. You can't use the full range of the device because it's not linear unless you programmed it like that and you did some other functions on it. So basically, there's 2 regions of operation. So I find this really interesting, but I don't know how useful and practical it is. But it's surely very interesting that you can operate your device here at about 0.5 millimeters gap. You can so basically how you use this device is that you start out with your target, you get really close, and you try to hit this maximum point here. So the max you program and you set the dial on the module such that the maximum voltage seen is 5 volts, and the voltage is reflection dependent. Depending on what kind of surface you're targeting, you're going to have a different amount of light coming back, different voltage. So you have to dial that into 5 volts, and then you dial it back down to this amount right here. With, let's say it's 0.35, 3.5 volts here. So you dial it, you pull your transducer away, or your probe away, such that it's 0.5 volts. Now you're ready to go. Now you have the sensitivity of 0.6 millivolts per micron. So now you can get now if you drive your device, assuming you're driving it in between a range of, let's say, 200 microns, between 0.4 and 0.6 millimeters away, so 200 microns, at that point you'll get an oscilloscope trace. Now if you have larger displacements, like if you go all the way down to 0.3 0.2 microns here, or 0.2 millimeters away from your target, you'll start to get some serious nonlinearity. But the cool thing is that, so there's one level of sensitivity here, and another level of sensitivity here. So I just find this really interesting, but it's not so practical. But in terms of what you want to achieve, but if you are looking for displacement, then it is a cheap option. And there are many types of devices, because you see there's only certain specific ranges. Like the vibrometer usually has several ranges already built in. This has a range built into the device itself, so you can't swap a card or press a button. There's no buttons on here that you're going to be able to press to change the range. You have to manually set it all up. So that can get kind of tricky, but as with any of these measurement systems, if you have a similar device you're measuring all the time, it's really not all that hard to set up a system. So somebody's asking, how much does it cost? So I've looked into purchasing myself, and I haven't. It's between 1,000. There's a lot of options. So but basically, you can say it's between $1,000 and $5,000. So you can purchase devices that are, like, they call them reflection independent, I think. And basically, there's not these two lines. There's just like one. There's just one curve. So it's like much easier to you don't have to what do you call it? You don't have to calibrate every time to that 5 volts per reflection. So that becomes easier. How would you calibrate voltage to displacement? So that's the fun part about displacement, and that it is you can have a dial. So if you want to do a real calibration to double check your manufacturer values, you could dial in 200 microns or so on your precision stage, and you'd be able to verify that indeed this is 200. Whatever. Let's say 1 volt of change is actually 1 volt of change is going to result in 100 microns or something. So you could actually dial it in, and you can verify that. Yes, with the vibrometer you can't verify with. You have nothing to verify with, which that's what I don't like about the vibrometer, is that you have no way of knowing if it's correct. You can't put it next to another system. But here you're really you're firstly with this type of, this is called, I think, a D-type sensor, they call it. The RC sensor is like the reflection independent. They use like two probes right next to each other in order to cancel out the reflection dependence. But in this one, there's not that cancellation. It's a little bit cheaper for that reason. And what else am I gonna say about this? And you have to find that maximum point and dial it in. That's how you calibrate. You don't necessarily have to look for the exact like point 0.3, like 0.25, I mean, oh, 0.25 gap. Oh, that's where I need to get 5 volts. No, you just need to look for where is the maximum, dial that into 5, and you already know you're at 0.25 when you're at the maximum. So there's a question here. Can we just ignore? This is a great question. Yeah, thanks for asking. Because that's what I've been doing so far. Because I do displacement measurements. So I'm not gonna say I don't do them. But so can we ignore displacement measurements if you have a professional simulation? So that's a yes and a no. The yes part is these are like the fundamental truths of finite element analysis and simulation, that if you have one of the truths, maybe I'll write an article telling everybody the truths of the law or the commandments or whatever you want to call them, the commandments of finite element analysis and experiments. One of the commandments is that if the frequency of operate, assuming that you have that you don't have like a ton of modes in your operating. If you're working like a 40 kilohertz mode or something like that, there's more than likely not going to be a ton of modes. Sometimes when you work with bending type devices, it's just a messier deal, so it's not going to apply there. But if let's say you have clean modes, one of the commandments would say, well, if you, it's not really a commandment, it's just like a law, I guess. However you want to describe it. But if your frequency of a finite element matches your frequency of your simulation, then you have agreement on what the mode shape looks like. Like the maximum displacement, the place of maximum displacement of your simulation is going to be the place of maximum displacement of your finite element analysis, and all the ratios will apply, like how much the back moves in comparison to the tip. Those ratios would apply both for experiment and also for simulation. So that would be, so the ratios of the amplitudes would be similar, and it would be the same between finite element and simulation. However, almost always the coupling factor of your assembled transducer is not what it says it should be in finite element analysis. It's always lower. So the coupling factor, basically the separation between resonance and anti-resonance. Um, um, if I ever make a rap video, I'm going to be going like this, I'm going to be talking about resonance and anti-resonance. If any of you guys know what that even means, we have an international crowd here, but I think it gets around. But anyways, I'm going to be going like this. What I mean by this is that the separation of the resonance and anti-resonance will always be smaller in your experiment than in your simulation. That causes a problem, and interpreting your current to displacement ratio that you measured in your finite element analysis to your simulation. However, if you were to somehow like adjust your piezo charge coefficient in order to match the coupling factor, that would be better. That would help. That would get you closer. So you nothing should necessarily stop you from getting some a better understanding, some type of calculation as to how much you're getting. So you may still have a current to stroke or current to displacement ratio, but you might have to adjust your modeling accordingly, and you should assume you're still in the ballpark. But it's not going to work so well when you're trying to do quality assurance. That's what that's not going to be helpful. But I think for like a research paper, if you wanted to be like, man, I really want to put a displacement value here, yes, by all means, for a research paper, go ahead and calculate it, but and with some of those adjustments. Anyways, let's keep moving. So yeah, let's go. Yeah. Okay. So here's another alternative to the technology of a traditional laser Doppler vibrometer, which uses a Doppler effect, which does take kind of different some different optics and digital processing. So here's what I'm going to call a digital vibrometer. So Polytech also does a digital style of their system, and I really like whenever I see somebody using a vibrometer, a scanning vibrometer, and they don't know what the analog signal looks like, I'm just like, I just do this a little bit. because sometimes there's like nonlinearity. For one client, I found a beat frequency occurring in their signal. I mean, and I asked like, okay, what is that? They said they don't know why. There's a beat frequency. So like there's like there's an oscillating envelope in their system. I don't I so but this is the but okay, that's just my take. That's just what I'm talking about. Okay, this is a different topic, but that's just kind of one of my annoyances in just point and shoot measurements. Like that's never good no matter what device you're using. You always have to verify that things are being measured correctly and there's not error in the signals. This is a little bit different. So this is a vibrometer which includes the data acquisition system in a single package. So again, like the package is this size. There's a cable coming out of it to your computer. It has the laser built in at the tip, and it has the data acquisition inside. So you have an Ethernet cable going back to your computer, which is streaming the data. The company that provides it, so they gave me one to demo, so I didn't purchase it, or I did not I wasn't given one for free per se. I'm kind of speaking independently, but I'm going to explain where I feel it has merit. So the company is Omni Sensing Photonics. It's a laser Doppler system. What I like about it is a lot of things. That it's relatively inexpensive compared to a laser Doppler vibrometer, a traditional one. So this is between as I understand, it's between $2,000 and $5,000 depending on your model. It's a point and shoot measure. Basically, you don't have to have an oscilloscope to do measurements or a separate data acquisition. So as I just mentioned, pointing and measuring is never a good idea if you're just like blindly doing it. But I mean, in terms of like what additional equipment do you need to measure vibrometer? Let's say if you only had one tool to know if your transducer is working well, maybe this would be one of those one tools that you'd use because it obviously tells a mechanical motion that you're really interested in actually. So there's no oscilloscope needed, so it's very compact. So this doesn't take like a lot of desk space, which is going to be great for verification environments where you're trying to verify operation of devices. It has a programming interfaces, which is good for kind of advanced usage. It provides both velocity and displacement, so you can record and stream data continuously. And I think this is where kind of at least the size factor is the next generation of devices, because I just don't see like a large equipment like this being the future of vibrometry or displacement measurements. I see, equipment like this being more of what I personally believe as an engineer as how far we've come. I believe that this kind of form factor just simply like kind of makes sense for what we need. It very strongly differs from this device. Not where it differs is that you don't have to get up close and personal. Like you don't have to get, if you see this plot here, so I'm going to zoom in a little bit. If you see this here, you have to get 1 millimeter away. If you're doing this, you have to get 0.5 millimeters here for measurement. If you wanted that really sensitive, you have to get like 100 microns away, which doesn't seem like so convenient. So this will allow you to have that same level of distance that you're typically used to from a traditional vibrometer, but you'll get you get the lower cost. So it comes with software that can help you analyze the data. So it's not analog per se. So I think there's also triggering options. So that's something to look into if the cost and the form factor are very important. To speak with the manufacturer, which is Omni Sensing Photonics. There's no software for scanning that I'm aware of. And you in order to do advanced functions, you'll have to use programming. There is a spectral analysis, as you can see here. There's recording, so you can kind of see an oscilloscope style view of the data. It identifies multiple peaks, so there's a lot of function there, but you won't be able to plug in like an oscilloscope or a spectral analyzer that you have externally, because the whole thing is just digital. So those are things to note there. And I see if any questions. Nope. All right. So here's one thing I do use and I do have. so it's a high magnification camera. It was first introduced to this method of measurement when I was working at a medical device surgical company, where they in those companies they very regularly use visual measurements of displacement, which is, if it's over a certain micron range, why not? You can actually tell a lot from what's happening there. It's also unique in comparison to other vibration measurement methods, is that you can actually see everything happening in real life. You're not going to get a measurement error here. It's clear as day whether it's oscillating or not. You're not worried about signal quality or level per se. You'll be able to tell very clearly whether your measurement is a good measurement or not, because it's visual. So what I like about this is some of the things that it does direct displacement measurement. It doesn't do velocity because it's just based off a blur. So there's a question, and I'm gonna jump back into that in a second after I kind of finish this part. Well, I'll just go into it. Why not? So if you're looking for abnormal modes by displacement measurements, you may just use impedance measurements. Yes. One thing here. So there's a couple of points here when you're talking about looking for abnormal modes. Meaning spurious modes where something is bending where it shouldn't be. It's not, or where there's actually maybe a defect caused by assembly, which would never happen in FEA, that then causes another type of oscillation. So yes, impedance measurements can also tell and also give you information on other types of resonances if they appear. Many times these spurious modes are not very well electromechanically coupled, so they will provide, in a small area, there'll be like a lot of oscillation. Let's say electrode resonance. It may be that the electrode is resonating but not very well coupled, so that electrode may fracture, but you won't really see that in impedance measurements, especially if you have a high damping situation. Either if the transducer is even high Q, but the application requires a lot of energy transfer, it's going to look like it's low Q because all that energy leakage in the environment, which is actually what you're looking for anyway. But so you may not be able to see that precisely. But mechanical is like very pure. It's purely mechanical, and you'll exactly be able to measure it. So yeah, I agree that impedance measurements are very good for transducer analysis, finding defects and spurious modes, but vibration is it's obviously more complicated to use, but it can provide a different type of information, which can be separate from impedance. And I think that cover. Oh yeah, the other thing I wanted to mention is that So when we measure impedance, you typically use a traditional impedance analyzer. But when you're measuring displacement, you're not stuck with a frequency sweep system, so it's sometimes easier to characterize devices at higher power using a vibrometer versus using a impedance analyzer. That's another thing there, because you can have your system hooked up to your actual drive and be operating and locked onto your frequency, then coming back and analyzing that. Let's say you have a nonlinearity that it's occurring, that you'd be able to kind of flesh out a little bit better using a velocity or displacement measurement. So yeah, it's a good question there. So going back to this high magnification camera, basically the way it works is you shine light on a certain portion of your transducer, and it reflects a little spot of light back onto the camera. When there's oscillation, it creates a blur, so that one spot becomes larger, and it becomes a blur like this over here. And you can actually measure. Let's go here over. You can actually measure the distance in pixels. You can have a calibration slide that you can convert pixels to microns, and so you can actually measure this displacement here. It can be the system needed, which is going to be usually like a machine vision or a digital camera with a high magnification lens. Which is the lens is called like industrial microscope. That's usually the terminology that's used, because for the industrial microscopes, it's not a traditional microscope where you're getting very close to a slide. You actually want some standoff distance so you don't knock your transducer into your lens when you're trying to maneuver it around. So it can be inexpensive, like this one I purchased here. I actually have this one. This is the one I use because if it works, and you can clearly tell it works because you have your evidence, you have your calibration, or you can actually use the kind of expensive one where you go on a kind of a more name brand website and you buy higher grade optics, which you will get a certain level of improvement. But it's really what you're kind of after that will determine which lens you need to buy and which camera you need to purchase for that. It's relatively low tech. It's just a blur. With the vibrometers and the light displacement, the device itself was responsible for providing the measurement. Now you are responsible for providing the measurement. You get this raw image data that you have to convert to a measurement. It can be cumbersome to do that, but it's also very useful. Yeah, the camera on phones as well. I haven't found the correct optics. I mean, the phone, the phones are very impressive in terms of their engineering. So and they're usually better. Any webcam, obviously, that you can purchase, your phone is better than any webcam you can ever purchase, which is a strange thing to me. But yeah, that's maybe the future is webcam ultrasonic transducer measurements. I'm going to quit my consulting and start that business. If there was enough need for it, that could be something. Anyways, I'm continuing, by the way. So it's 2D visualization. So you can actually get these patterns that occur depending on, sometimes transducers are intentionally off center, like in terms of their needle, in terms of how they're constructed, so they can actually produce like S curves, figure eights. Like there's very complex patterns that can be seen with this. Whereas with the traditional vibrometer, you just get one measurement and phase back. That's what you get. Here you actually get 2D kind of displacement data. And there are vibrometers that do autoplane measurements. So that is something I haven't used. I've not covered it here. It's one of the Polytech versions. It's pretty expensive, but it could provide something very similar to what I described. This wouldn't be the only the only measurement method that can do it. There's also the out-of-plane displacement measurements that also would be necessary if you're doing a torsional transducer to have that, because that's all kind of in its own axial plane. You won't really get much from the much from the single point or traditional vibrometer. Uh, so you can easily measure small targets. It's already a microscope built in. And you can measure very high displacement and velocity, and there's no bandwidth limitation for that. So it's not bandwidth limited, but it is displacement limited. There has to be, at least from my experience, over 5 microns of displacement, or you cannot make a measurement at all. You can't be driving your transducer with like 1 volt and expect anything to measure anything except just what you started with. So you actually have to use a higher voltage, which is kind of nice because it forces you to characterize your device and with a voltage in a environment where you'd actually be using it. You can also do this very easily underwater. That's where medical device folks like this. It's very easy to apply this visual measurement underwater, where your optics are outside of a water chamber and your measurements inside, so you can kind of adjust your field of view to that. The setup isn't hard if you're measuring the same thing over and over again, but if you're measuring new things, you may need to experiment with your lighting. You'll need to experiment with how you're holding your transducer, and the whole setup like that. And it's not there's no analog here. I was doing a short project where I was trying to convert automatically this, take webcam images and convert them to using LabVIEW to displacement values. If somebody's interested in that, you can contact me and I'll see what I can do for you. But it doesn't readily transform into displacement values. What I don't like about this is that lighting can be tough. It's cumbersome to take a measurement from an image. Just like draw a line and do conversions. There's no phase data, and you can't do low displacement measurements. Sometimes it's convenient to use lower voltages to start off with, but you can't do that. And as you increase in your amplitude, you'll increase in your ability to measure more accurate data. So you're going to be measuring the 10 to 20 micron range is not going to be near as accurate as 100 to 110 micron range. That's going to be much more accurate percentage-wise if you're measuring a larger signal, which is very problematic if you're doing, high frequency devices. Like good luck getting a megahertz device to go like 10 microns. Like good luck with that. It's not really going to happen there. But lower frequency, like lower than 100 kilohertz, if you have significant displacement, if you have a bending device, this will work. So here is kind of the summary slide, and I'll just kind of go along here. Here's the Polytech, which I'll just say it's a stand-in for all laser Doppler vibrometers. It has a high frequency, like about 3 megahertz for like let's say a standard model, but they have a lot of specialty equipment that goes like 20 megahertz and maybe even higher than that, and the cost can start sort of low, but it goes really high after that. So there's analog with digital options. So they do sell data acquisition, which would probably cost you another arm and a leg from what you started with. So you only had one arm, one leg left after you bought the first part. You'll have none after you buy the second part. So, but it's relatively easy to use, I would say. I guess that's because I've used it a lot in the past. The photonic sensor, which is light displacement, so light first. Some standard models go to 300 kilohertz, some up to 2 megahertz. So the bandwidth is an issue here. If you want high bandwidth, you can't use this. There are a wide variety of prices. One retailer sells it for 20K, and the Philtech, I just put around 3K for the device. So there's analog with some digital options, and I think it looks to me like it's hard to use. But that's just from my point of view. Then the other one is the high magnification industrial microscope. The principle is you get blurred images from long exposure. It's displacement first, but you have to have a certain level of displacement in order for the thing to work. You can have a wide range of cost. As I mentioned, I'm using one that I purchased for about $300. However, and if you calibrate it, it works. I mean, it is the measurement. You see it, but you can also purchase, I guess, higher grade optics and cameras for larger sums of money. You get analog data without any phase data, and I would say it's hard to use, but obviously none of these things are impossible. The last part, and I'll describe the laser Doppler vibrometer, basically the digital compact vibrometer, and I'm giving the example of Omnisense Photonics. I think they might be the only one who sells a similar device. Their bandwidth is kind of more sampling rate dependent, so their maximum sampling rate is 5 mega samples per second. That might get you to about 500 kilohertz if you're talking about one measurement per or 10 measurements per oscillation cycle. The cost is less than 5,000. They do have some options, but just to know that it's much less than Polytech, and it's also maybe comparable to the Philtech device. So I would actually kind of lean toward more the Omnisense Photonics if you're looking for something compact or something more inexpensive, or something just like, I don't want to use an oscilloscope. I don't want to. Maybe some mechanical engineers have issues with oscilloscopes. Like they never use one. I never could understand it. I don't want to use it. I would say you're pretty biased at that point if you're saying all of that as an engineer, even if you're mechanical. But if you still insist you want something directly straightforward, maybe something that the assembly folks can use, the quality folks who are kind of measuring devices on the way out, then this is a good solution and option. So here's kind of the verdict. The Polytech device, I think it's best as a research. If you're buying something for research and you don't have a budget, like you have a large budget and you want all the information, then or you have a very specialty application, high frequency, or microscope, for example, MEMS device, then you might have to go with Polytech. That's just or a similar company. If you want cheap light displacement measurement, I would say then the Philtech device is the right one. If you want direct displacement, you want analog, that's another part. If you want analog light displacement, a direct measurement, then that would be the one for you. If you know you have large displacement and you're measuring it like in a water chamber, or you need something that's relatively inexpensive, you just want to verify that things are oscillating, then I think the high microscope camera will work well. Or if you want to measure a complex displacement pattern, that's also going to work well if you're measuring bending and longitudinal at the same time. For me, price was the biggest reason why I use this, but it is limited in the sense that it doesn't have high frequency. It can do high frequency, but it has to have high displacement, which those don't go well together in ultrasonics and in life in general. High frequency and high displacement is not going to it doesn't play just because of the physical rules. Um, for the OmniSense Photonics, it's kind of a unique device. It combines a lot of the attributes from all of these. I like the fact that it's inexpensive, and also you can have a standoff distance, and you don't need an oscilloscope, which can be a plus and a minus. Like, you might want to put it into oscilloscope, but you also might not want to if you just want to have a simple test that an assembly worker does at the end, or if you want another way to verify your transducer is working, and it's not important to you to put all those waveforms together. You can still get a displacement, a milliamps per displacement method out of it, and you can also get a lot of you can get all the analog data, because it's not just going to say 5 microns. It's going to say, it's going to give you you can actually record the entire waveform, so you have a lot of detail on that. Here are other mentions. Like, there's not just vibrometry to measure oscillation. There are other ways to measure mechanical energy. One interesting point, I haven't been able to use this myself, but I am meaning to do it at some point, is to use an ultrasonic microscope. So although and there are ultrasonic speakers, but there are also all the transducers that oscillate in ultrasonic frequency are emitting sound waves. So assuming you have all your holding placement constant, you would be able to use an ultrasonic microphone in order to measure the pressure coming off of the transducer, assuming you have a very consistent standoff distance, and there are probably a couple of other things you need to consider. But it is an option that you can use. And I've seen very old papers published by the military where they used microphones to diagnose the spurious modes of wire bonders. I have it in one of my emails or one of my blog posts I did a while ago. I referenced that paper, that kind of military paper published by the U.S. military about that. If anyone's interested, you can put it in the chat, and I'll kind of resurface that for everybody. But that was kind of interesting how the old school folks did it, and how we need to learn and remember all that. So here's an animal ultrasonic microphone, but other MEMS option exists. Just because microphones are designed for 100 hertz to 20 kilohertz, it doesn't mean that they can't go higher in frequency if the correct considerations are made. So you can use a piezo element as a sensor by bonding it to a part of your device. You can also use a hydrophone, which measures pressure underwater, kind of like an underwater microphone. You can have an application-specific device or measurement system just to make things very consistent. So the consistency is the point of this. Obviously, I assume most applications have their own measurement and quality assurance methods, but to be very specific and more scientific than actual application would be, in order to get consistent information on the operation of the transducer versus just only the final performance, which also would have a lot of other environmental factors, even if you try to standardize it. The last is current and power. This is don't let me catch you measuring vibration without measuring current and power. These are the first two steps, the first two parts, as somebody mentioned in the chat. Like, you can just do impedance measurements and get a lot of information, and it's like only 2 terminals, and there's not a whole lot of things going wrong, and it's kind of very central to a good measurement methodology for understanding your device. So I will actually now stop the recording here.